extensions of the fundamental theorem of calculus. Some applications of this fundamental theorem of calculus include the following. Number one, area, or net area as we've been calling it and working with it. Number two, something we haven't talked about yet, accumulation, or total change. This is when we integrate rates of change. For example, first one, if capital P of t equals population of people at time t, then capital P prime of t means, well, this is derivative, and derivative is rate of change. So this means the rate of change of P, which stands for the population of the people at time t. So this is the rate of change of the population at time t. So P prime of 5 would be the rate of change of the population at time 5. The integral from t sub 1 to t sub 2, 2 points in time, of P prime of t dt, well, using our fundamental theorem of calculus, when I integrate the derivative, I get the antiderivative. The antiderivative of P prime of t is P of t, and it's evaluated from t sub 1 to t sub 2, which means it's capital P of upper limit t sub 2 minus capital P of lower limit t sub 1. Well, think about what that represents. This is the population at a later time, let's say the year 2015, minus the population of an earlier time, let's say the year 2000. So let's say the population of people in the year 2015 was a lot more than the population of people in the year 2000. The difference between those populations represents a total change of the amount of people in that population. So this represents a total change or a total accumulation of the amount of people from time t sub 1, whatever that may be, to time t sub 2. Let's look at another example, B. If S of t equals the position of a moving object, then S prime of t equals, well, again, that's derivative. That represents the rate of change of the position, which is more commonly known as the velocity, or v of t, as we like to call it with our symbols. So what would the integral from t sub 1 to t sub 2 of s prime of t dt be? Again, if this is a derivative and I'm taking the integral, that means I'm taking the antiderivative of the derivative. That leaves me with just s of t evaluated from t sub 1 to t sub 2, or rather, the position at time 2 minus the position at time 1, or better known as the change in position. Change in position has another name. It's called displacement. Keep in mind that another way to say s prime of t is to say v of t. So this could say the integral of t from t sub 1 to t sub 2 of v of t dt represents the change in position. Now, a couple of important points to note. As a summary, total change on A to B is the integral of the rate of change. Displacement, or the change in position, which is just an application of this, is the integral of the velocity. And also really important to know, the total distance traveled is when we integrate the absolute value of the velocity. Because we're not just finding the difference between the locations, the difference between the positions, the position at one point in time minus the position at another point in time, but rather we're adding up all of the movement that took place, not just where we ended minus where we started, but we have to add up all of the movement that came in between. And the only way to add up everything and not have to subtract is when we're making it positive, hence the absolute values. That enables us to add up all of what was traveled. From a free response question on an AP exam, a metal wire of length 8 centimeters is heated at one end. The table gives selected values of the temperature T of X in degrees Celsius of the wire X centimeters from the heated end. Find the definite integral on 0 to 8 of T prime of X dx and indicate units of measure. So remembering the fundamental theorem of calculus, this definite integral using our fundamental theorem means the antiderivative of t prime, which is t, evaluated at the upper limit, minus t, evaluated at the lower limit. Remembering our fundamental theorem and being able to write that, we can now use our table. What is t at 8 centimeters? Well, here's the values for t. At 8 centimeters, it's 55. T of 0, here's the point where x is 0, the t value is 100. What does that give us? Negative 45. Indicate units of measure. Well, what are these t values in? It tells us in the directions, degrees Celsius, so negative 45 degrees Celsius. What does this mean in terms of the temperature of the wire? Well, remember that the definite integral of the derivative of a rate of change gives us a total change of that measurement. So in this case, this is a total change in the temperature. Well, how is it changing? It's negatively changing. That means it's decreasing. So we can describe this by saying the temperature decreased, right? Decreased because of the negative by 45 degrees Celsius. And when did that do that? Over the 8 centimeters of the wire. Always think about the situation and what's happening in the situation. So we could say the temperature changed by negative 45 degrees Celsius, or we can say decreased by 45 degrees. So the decreased is from the negative of the 45 degrees Celsius. One more. Dry ice puck is pushed back and forth across an uneven surface. This is a graph of its velocity in centimeters per second as a function of time in seconds. Determine the displacement. So I want the displacement, or the change in position, from 0 to 10 seconds. That's going to be the integral from 0 to 10 of the velocity with respect to t. This means the net area under the velocity curve, or between the velocity curve and the x-axis. So 2, 4, 6, 8, 10, that's the end of the picture. We'll just make sure. And then we're going to evaluate the net area. So I can break this up into a bunch of shapes that I see. A triangle perhaps at first. So this triangle, notice that the y-axis is counting different from the x-axis. So the base is 2 while the height is 40. So 1/2 of 2 times 40 is my first little section there. So that is an area of 40. Then we've got this rectangular section next to it. If we don't want to use trapezoids, we've got this rectangular section in here. That rectangular section is just length times width. So that's 3 blocks times 40. So 3 times 40, or 120. Then we've got this little sliver of a triangle right here, which has a base of 1 and a height, again, of 40. So that little guy is 20. Then we've got a little triangle here and another one that's the exact same size right here. So each of those little ones is half of base times height, or half of 1 times 20. So each of those little ones is 10. So that's also 10. We've got this little rectangular section right here. That one is 1 times 20. It's just a rectangle. And then finally this little triangular region, I should have noticed that was the same as the other ones that are 10. So that one's also 10. So as we do our net area, we are saying anything above the x-axis, all of those areas. So 40 plus 120 plus 20. And then minus whatever's below the x-axis, so minus 10, minus 20, minus 10, and then plus that extra little one at the end. So again, noticing that we are subtracting, subtracting, subtracting all of what was below the x-axis, all that region right there that was below the x-axis. Okay, everything below the x-axis, we're subtracting that and get a final value of 150 centimeters. How is it centimeters? Well, we're multiplying the x-axis times the y-axis. The x-axis is in seconds and the y-axis is in centimeters per second. Therefore, centimeters will be our units. Finally, we're looking for the total distance traveled instead of just the displacement. That will be the absolute value. We want to add everything. We don't want to take away what's going backwards. So instead of subtracting any of these, we are adding all of the areas. So plus 10, plus 20, plus 10, all of them this time, all of them positive. Anything that was below the x-axis, all positive now. This will give us a total of 230 centimeters.